So we start the session. Nagaraju Y is a research scholar working in the Department of Computer Science Engineering. His area of research includes deep learning, machine learning.
में आप आ जाओ। मैंने कहा नहीं, वो अभी सर से बात करनी है, शायद एक डिसाइड हुआ है।
Participants, unmute yourself. Sorry, mute yourself. Do not unmute yourself, okay, in between.
अरे नमस्कार भैया।
Okay. Yes, sir. We'll continue our discussion. So Nagaraju has published several research papers on deep learning, particularly in classification and segmentation of objects using deep learning models. Over to you. Over to Nagaraju.
Thank you, sir. Thank you so much for introducing me. Is my audio clear? Is my audio clear, sir?
Yes, audible.
Okay, thank you. I'm going to share my screen now. Is slideshow visible, sir? Sir, is slideshow
Yes.
visible?
Yes.
Is it moving?
Yes.
Okay, thank you. Good morning, everyone. So myself, Nagaraju from UVCE, actually I'm a research scholar working under Dr. Ventesh, sir. So today we are going to discuss about introduction to CNN. It is not mathematical oriented. It is completely visual introduction how CNN works. So after this, we are going to see what are the learning techniques we have in machine learning, and as well as we are going to use in deep learning. So later on, we will see architectures, and at the end, I'm going to do answer session. Okay, this is my flow of presentation. Let's start with the. Sorry, 1 minute. I'll just arrange my screen. Okay, so I'll start with the history of CNN, how visual system evolved. Then I'm going to discuss about convolutional networks and the building blocks of convolutional networks. Then how it works, the example of animation, then how filters works, and we'll see learning techniques. Then in a second session, we are going to see today's second session. We're going to see about classification models, object detection models, then segmentation models. After that, I'll show how to classify apple and grape leaves in Colab. Okay, that is actually based on transfer learning. Let's start with our today's session. Okay, so if we and one more thing I want to clear. So what are the images I have used in my PPT is from Google, and my discussion is computer vision oriented. Okay, it's completely about images, and that's why I told it is about computer vision. Okay, so if we look at how visual system evolved, okay, so it goes back to the 1960s, where researchers are doing research about where to know how visual system works. So among the many researchers, Hubel and Wiesel succeeded in understanding how cat and monkey visual system works. Okay, how cat visual system works, how it reacts, how cat brain reacts to particular image, and which particular signal is going to trigger, and all those things they understood. Then, because of their work, today we have many models, and we are moving towards the computer vision world. So both of them studied about how a cat system works. They were successful understanding of the visual cortex, and ultimately for this particular work they got Nobel Prize in physiology. Okay, and then using this work, both of them, they introduced a model called as cascading model. A cascading model they proposed, which consists of simple cell and complex cell. So we'll be seeing in the next slide what is complex and what is simple cell. And the persons who are going to, the researchers who got triggered and they inspired from this work, they started to work towards the visual systems, that is vision missions. Okay, you might have heard the word machine vision. Okay, so then comes, after this, if we consider only in convolutional networks, then comes model called as neocognitron. Okay, neocognitron. Actually, there is a debate. Somebody says, some people says this is the first convolutional network. Some say it's not a first convolutional network, but still, it is the first convolutional neural network introduced by Fukushima in 1980. Not exactly 1980. It is late 1970s and early 1980s. Okay, so what they did is they got inspired from the work done by Hubel and Wiesel. Okay, got inspired and they introduced this neocognitron, and this particular model was used for recognition of Japanese characters. And as I told, here they have used the cells or the model, cascading model introduced by Hubel and Wiesel. So he's going to use, Fukushima is used complex cells and the simple cell, where you can see this S cell says it's a feature extraction phase, and C cell, that is complex cell, is a pooling cell. And then they're going to perform classification. So how it is going to do? So I told, this is the first convolutional network, and it serves as a inspiration for many other convolutional networks. And we'll see how it works and how convolution works. And I'll say about how this convolution layer and pooling layer is going to work in the next slides, upcoming slides. Okay, and you can tell that it's an extension or a extended work of the cascading model. So then comes, we all know the word LeCun, Jan LeCun, who is the pioneer of, is the one who invented the convolution network, in a sense, deep convolution network. Okay. So now, again, it's a history. I'm not going to discuss about LeNet here. LeNet is not a first one they introduced. Actually, in 1989, they introduced something called as ConNet. Okay, ConNet. This is the first model they introduced, and they adopted backpropagation technique, and that model was particularly for identifying or recognizing handwritten zip codes. So after this, we have one more model. That model is actually called as time delay neural network. Okay, time delay neural network, where this is the first model is used. They have used the technique called as gradient descent. Okay, this model is actually given by Weibull. Okay, is a person who gave this network. And again, this is not like eye-catching work, but the major contribution from this work is gradient descent. They have used and they showed with the world how to make use of gradient descent technique. Then in 1998, Lee Kuhn and others, they introduced model LANET. Actually, it is not LANET, it is LANET 5, because from the year 1989 to 1998, they were doing many iterations of LANET. Okay, the concept is there, no? They tried and tried and tried. They finally arrived with the model LANET. So this is the model they have used, and many people used, and many business sectors used on the time to recognize handwritten digits. So the success of this LANET was in the banking sector. Okay, where banks were using this LANET to identify handwritten digits. Okay, handwritten digits on text. Okay, handwritten digits on the text. But even though they have succeeded in identifying or recognizing handwritten digits on text, even though the accuracy was very good, the CNN started to fade out. Why? The reason is very simple. If you look at the deep CNN or deep convolutional networks, this type of networks always requires higher computing machines. Okay, first column was computational requirement. Okay, after this, so CNN always requires, okay, apart from few techniques, learning techniques, it always requires huge data. So at that time we had no data sets. So if you want to do research, then you are responsible to collect data. So the constraint of computational requirement, constraint of huge data requirement, and one more thing is hardware problems. Say for example, nowadays we have very good like GPUs. At that time we had no GPUs, and those even like the processor we had were not computationally effective. Okay, this is the reason why the CNN went off like fashion in that time. So I'll continue this discussion in the next session. Okay, so I'll move on to the convolution neural network now. Okay, what are the building blocks and what we need to understand to like build our own network, and how convolution works, and what is subsampling layer or pooling layer, and how this classification happens. I'll continue this next session when I explain classification models. Now switch back to convolution network completely. So as I told, it's very important to understand. Each and every layers of convolution networks to create our own models. So as like told by our previous resource persons, yesterday by Gayatri madam or Deepika madam or Venkatesh sir. So we are going to use filters. We are going to use many other things, even activation functions. So if you look at this image, okay, if you look at this CNN network. Okay, CNN model. What you can understand is we are going to give an image, and this network is going to classify what is the given image is. Is it so simple? If anyone looks at this, they say it is simple. We just give an image input, and we have CNN here, and you will get output. But it is not just give input and you get output. In the back end, we are we are doing so many things. Reality is different actually. So here we have extraction phase, we have classification phase, we have activation function, which is going to trigger whether the particular neon is going to be considered for classification or not, or it has to be moved to next layer or not. Like that, they're going to decide how to choose a particular weight. Okay. And now we'll move to next. So to understand how CNN works, it is must to understand how computer see an image. Okay, then how convolution layer is going to work and how pooling layer is going to work. Then all the hyperparameters we need to concentrate on, to fine tune, to increase our model's accuracy. Then we understand what is activation functions. Okay, then we have flattening layer, we have dense connectivity layer, at the end we have classification layer. Okay, let's see one by one how it works and how it happens. So how computers see an image? Very important, right? So it is very important to understand here one thing, that whenever we give image to CNN, okay, it is in the form of digital matrix. It is just a matrix of numbers. It is representing an image. Okay, here we have, see here, we have a image of R, letter R. If we convert this image, or if we give this image to CNN, this is how it look like. This is how it look like once it is converted into digital image. Here, make sure one more thing. Here 0 represents white cells and 1 represents black. This is okay. So you can see here, where and all black pixels are there are ones. 0, I mean, if white is there, for example, this region, you can see this region is 0, it's completely 0, and surrounding also 0, and here is 1. Okay, this is how it is going to convert. This is how it is going to convert image into a normal image into digital image. Okay, so we have one more example. Here I have taken X into consideration. You can see here, wherever black pixels are there, we have ones, and you can observe in some places we have 4 ones and some places we have 3 ones. It depends. While converting an image into digital image, it varies. Okay, here I have used some online tool to convert, so that is why it is not proper. But still, it depends. Sometimes what happens, say for example, if I zoom in this particular image, we will get some blurred black pixels next to this edge. Okay, those edges also will get values here because that is also a black pixel. If I zoom in, I'm telling, if we zoom in this image, we will be having blurred pixels, black pixels. Those pixels also gets the value here. Okay, that's why we have extra ones here, or lesser ones here. So next, so this is how convolutional neural network look like. Okay, where we have this is the image. Just now I told this is going to be a digital image. Okay, so when we give this image to convolution neural network, it is going to use convolutional layer extract features. Okay, that's why this phase till the flattened layer before, before this layer till the end of the last pooling layer, we call it as feature extraction phase. Okay, then whatever we are seeing here, fully connected layers or dense layers. Okay, this phase is called actually classification, and then from these layers we are going to get some probabilities, and the layers here, the nodes are going to code or give probabilities for each and every labels. Based on the probabilities, where the model is going to decide what the given image is. Okay, in feature extraction phase, we have convolution layer, we have pooling layer, and we have ReLU also. We are going to see in an upcoming slides. Then here comes flattening layer. Okay, so now let's discuss one by one. Okay, what is convolution, how it works, and how pooling works. Okay, so here we have a matrix. Okay, here we have matrix, and okay, this is a matrix, input matrix. This is actually a filter, and this is going to be a feature map. And one more thing, if you have doubts, you can leave your questions in chat box. I know you are not able to unmute yourself. Okay, so now this is our input for our convolution layer. So this is our filter. Is going to be used for the purpose of extracting feature from this input. So a filter or one more word we use is a mask. And okay, not mask we use only in terms of classification, and don't use the word mask. Mask or kernel, use mask or kernel. Okay, both are same. So in CNN, filters are not defined actually. Okay, the value of each filter is learned by CNN only, and it is like a black box. No one knows what is going on. It is going to learn, and it is going to define what is the values of particular filter. And then what we will do is we are going to roll this filter across the image. Okay, across the image, and we are going to perform convolution. Okay, actually yesterday Venkatesh sir told about convolution operation, how it works. Okay, we will apply this filter to this region, and we are going to perform convolution operation here. How we are going to perform? So this is how we perform. We are going to multiply the pixel value or the cell value of the filter with the cell value of the input where we applied the filter. Okay, you can see here we are multiplying 9 with 0, 4 with 2, 1 with 1, and 1 with 4, and 1 with 1, and 1 with 0. Like this we are multiplying, and at the end we are going to add up all the values, and we will get one value. That value will be the output, or that value will be the pixel of the feature map. Okay, pixel of the feature map. So wherever we apply filter now, that region is called as actually receptive field. Okay, receptive field. So and one more thing, this convolution layer is going to the operation itself tells that we are going to extract spatial features. That means local region features. Okay, so if you apply a 3-cross-3 filter, we are going to get so and so size output. I'll tell in the upcoming slides how to calculate that. Okay, that's why I'm not telling what the size of this output is. So here it is also a matrix, and the output is also a matrix, but it is called as a feature map. But here we are doing 2D convolution. That means we have only like width and height. Okay, that means we are applying filter on one particular channel. Okay, what if the input is color image? We all know, right, how color image look like. So it is actually a RGB channel, right? It is actually a RGB channel. So the RGB channel makes an image in reality 3D dimension when we work with convolution layers. Okay, then how to perform or how to extract features out of the 3D image? That means it is a 3D image, three channels image. How to extract the features out of 3 channels image? How to perform? It's very simple. Here we have an assumption. So this is actually our input. Okay, this is our filter. Here we have an assumption. So whatever filters we are going to use for extraction of features on RGB images are of form volume. That means the size of filter is different, but still the depth of filter is equal to the depth of the input image, or sorry, input matrix or input feature maps. Okay, that means if you have RGB image, then whatever the filter we are going to apply is of the form volume. So now we are going to apply the filter onto this image. Okay, so this is actually 3D now. It has 3 channels. Even we have 3 channels. This 3 channel filter is going to be applied on going to be applied on this particular image. Okay, since it is a RGB, we are not talking about filters. It's going to extract. It is going to extract features out of all the channels, and it is going to create. I mean, it's going to give output for one pixel. That means we are going to convolve, or we are going to move this particular filter across the image along the channels. Okay, across the image and along the channels, we are going to extract the features out of the given input. Okay, here output is same. So whether you apply a convolution for 2D image, that means only a channel, or 3 different channel 3D image, output is going to be 2D. Okay, output is going to be 2D. Why it is 2D? Because see here, all here in the previous slide I told that the kernel is going to extract spatial features, but in this case, kernel is going to extract spatial features as well as cross-channel features. So whatever the filters or whatever the operation we are doing in real time right now, okay, right now is actually like this. It's going to extract spatial features as well as the cross-channel features, and it is going to give one output. Okay, that's why we have. I think some of you might have heard about depth separable, depth-wise, point-wise, and like that. Many other variants of convolution networks are there. Convolution layers are there. Okay, so it is going to combine and is going to give one output. So again, it is a 2D image. Then why we have different like when we look at the convolution network, we will be having like this, no, behind this particular like feature map, will be having many feature map. Why we have like that? It is because it is not one filter we are applying on this particular image or the input. We will be having many filters. Okay, many filters are going to be applied, are going to apply on the image to extract the features. We are going to apply many filters to extract the features out of this input image. Okay, so each filter we are going to use will give output of type 2D. That means this filter is going to give one feature map. Like that, if we have 10 filters, so 10 filters are going to give 10 feature maps. Remember, this is very important to understand hands-on also. So 10 filters are going to give 10 feature maps. Okay, so that's why as the convolution neural network grows, we'll be having, the depth of the convolution neural network will increase. Okay, we will be having as many feature maps, as many filters we use. And each and every filter will be having its own characteristics and its own responsibility. It is going to extract its own in its own way. Okay, so some of the filters, like yesterday I told by Gayatri madam and Deepika madam, they are given example of elephant ride. So one filter may extract trunk, and one more filter may extract the tail and backbone edges. Okay, like we can say horizontal edges and vertical edges, and like different combination of both, like that. It is again a black box. No one knows how it is happening, but we can see how it is happening. I'll show in animation how it is happening. We don't know what the filter is. Okay, so the next thing is like how we apply filter on a particular image or input. It is always going to be like we start from left side top corner and we move towards right side, and we come from we go like this, like we go right and come back to left, and again we go right and we come back to left, again we go right till we reach bottom right corner. Okay, in this fashion we are going to extract or we apply filters, okay, to extract the features. So this is the step 1 and step 2 and step 3, step 4, like this. You can observe here the movement of the filter. So it was here in the first step, and the second step it is here. Okay, so the movement or the interval at which we apply filter, okay, the filter on the image or on the input, given input, is actually called as stride. Okay, so based on the stride, we are going to move filter forward. Okay, so this is about how we move filter across the image. So here comes pooling layer, next important layer in convolutional networks. Actually, pooling layer is also called as a downsampling layer because pooling layer is used to reduce dimensionality of an image and is not going to affect, or it is not going to learn anything. It is not going to learn. It is actually parameter free operation, and it is not going to affect depth of the image. But for sure, it is going to change dimension of the image input. Okay, whatever the input we have, that dimension is going to be changed, and it preserves the features that are very important for upcoming layers or higher level layers. So let's assume this is the filter we have. And sorry, 1 minute. I'll turn on the charger. This is the filter we have, and we have 4x4 input here. If we perform pooling operation on this, we are going to get some output. That output always depends on stride, and filter size. Don't worry how if I tell the output is 2x2 and it is going to be like this. As I told, I'll explain how to calculate this in the next upcoming slides. So my intention here is just to explain pooling layer. Before going forward, one more thing I want to explain, that is in pooling we have two different pooling types, okay, or ways. One is max pooling and one more is average pooling. So what is this max pooling? The max pooling is like where we apply filter, okay, like this. When I apply filter on this place, okay, it is going to take maximum value among these values, and it is going to reflected in the output filter. Okay, so this is how it is going to happen. See, we have output plus to output. So among these values, we have one as maximum. Here also one is there. So maximum value is 1. I'll take 1. So I'll move my filter to next position. Okay. So in this place, in this receptive field, actually maximum value is 0 itself. We have no other values than zeros. So we are going to consider 0 as a value. So I'm going to place it in a feature map. It means output. I'll move my filter to next position. So here also 0 is our maximum value, and we will move our filter to next position where again the maximum value is 1. But you can observe one thing here. Actually, purposefully I have taken an image which represents backward slash. Okay, if it is black color slash in an image, 4x4 image, this is how a matrix look like, correct? So when we reduce dimensionality of an image, okay, using pooling layer, still we have backslash in the output of the pooling layer. This is how it is going to preserve the features, and it is not going to update any of these values because as I told, it's parameter free. We are not learning anything. The CNN is not learning anything. It is just reducing the dimensionality of the image, the input. But why we need to reduce? Why we need to reduce the dimensionality of the the input? Why we need to do this? It is because it is very important, and to minimize the computational complexity and to the time taken to learn the image. Okay, it is very important reduce the time taken to learn image features. So if we have same image input size, same size input for each and every convolution layer, number of parameters going to be huge. Okay, for example, if it is 4x4 cross B, then 4x4 is 16. 16 cross 3 is 48. Okay, it is going to be huge, correct? I mean, here it is only 48, but what if we have like 224 cross 224 or 448 cross 448, or if it is 1000 cross 1000, value will increase. So this if it is convolution layer, then convolution layer has to learn 48 parameters. Okay, that's why to reduce complexity and to reduce number of parameters in upcoming convolution layers, we are using pooling layers, okay, to reduce the number of parameters by reducing the dimensionality of image. Okay, I hope clear for everyone. And again, here also the interval at which we apply this filter, okay, the filter again depends on stride. Okay, usually in pooling layer, we are going to use slide as 2 generally, okay, because our intention is to reduce dimensionality of an image, right? So we are going to use slide as 2. Okay, clear? Sorry. So next we have one more pooling operation, that is average. Okay, one more pooling operation, that is average, where we are going to apply filter here like this. Okay. So the difference between max pooling and average pooling is, here we take maximum value, but here we are going to add up, okay, all the values, and we take average of values. Okay, we take average of these values and we'll update here. And again, we move our kernel to here, filter to here. Again, we take this and we update here. The same thing. If it's slide 2, we are going to get a 2x2 image. If it is slide 1, then we are going to get 3x3 image. It's as simple as that. It depends on slide and depends on the size of the kernel we are using or the filter we are using. Okay, next comes, after pooling layer, next comes padding. So I think everyone knows, if you are at least studied at least one paper, you have come across convolution layer, pooling layer, padding. Okay, this is what the padding is. So why padding? Why we need padding? Situation is very simple. In some situations, we don't want our image to be smaller one. That means we don't want to reduce dimensionality of an image. Okay, shrinking is not necessary. Okay, not necessary for us. And this is one case, and one more case is, you imagine we have an image. Okay, we have an image, and important part of the image, or the what we want exactly, is here, somewhere is here and here. In the corners of the image, we have features which are very important to be learned by a CNN. In that point, if we apply a kernel here, okay, it is going to say, for example, the small, let's say, for example, this is a small feature, but we have a large feature here. Let's take an example of plant leaf diseases. Okay, here we have darker lesion here, and here we have dots. Same, the image is suffering from the plant is suffering from thumb disease. We have taken the image or photograph of that leaf, and the leaf is again suffering from same or different diseases. Okay, if we take different diseases, here we have one disease, a dot, and here we have one more disease which is very bright or a larger lesion. Here it is a lesion is very small. Okay, but if we perform convolution on this type of images, what will happen is, the dark spot, okay, larger dark spot is going to be highlighted, and whatever the smaller dark spots or lesions going to be ignored. So what to do now? How to overcome this issue? So to overcome this issue, okay, they introduce something called as padding. Okay, padding. So you can see here, in case of if we don't want to shrink our image, okay, first example is not shrinking. So we have 4x4 image. So we have 3x3 filter, and we are applying, and we are going to get output like this. Okay, but we want output matrix same as the input matrix. Then what to do? Just add the image with zeros like this. Around the image, you just add with zeros. Okay, when we apply here, you can see here it is going to be applied on this particular receptive field. First, then it moves, then it moves, then it moves. So we are going to get the values. But if we pad the image with the zeros, then you can see here it is going to be applied like this. Okay, that means in this region we are going to apply. So that means here we are going to apply by ignoring. I mean, we are not ignoring. We are overcoming this issue actually. Okay, so this lesson is going to be highlighted first. It is going to learn. Then it moves. It moves. It is going to learn here also. Okay, again it is going to learn here also. It's going to learn here also. So successfully by adding an image with zeros, we have learned. Sorry, CNN learned the small lessons also. Okay, small lessons also. So here we have in padding we have two different types of padding. One is valid and one more is same. What is valid means? This is actually valid. No padding at all. Okay, no padding at all. Zero padding it is. Okay, and we are not going to add any values around the image. So we have one more padding that is the same. So here we are going to add zeros around the image and we are going to perform the operation. Okay, so this is how the padding works, and the importance of padding is prevent image from shrinking and to we need to preserve some features of the image in the other two in the edges of the image. Okay, so this is what the padding is. Then, so these are actually a convolutional neural network look like, correct? As I showed in the beginning. So we have filters, multiple filters, and we have the input. This is the input image. This is the filter map, and we are performing max pooling. Then here we have something called as flattening layer. What is this flattening layer? So at the end, after the last pooling layer, we will get matrix like this. Okay, matrix like this. So let's take values randomly. Right, this is how we will get. But how dense layers are going to get going to accept the values? They're going to accept like this. We have different nodes. Each node is going to accept single value. It is not going to accept a matrix. So what to do now? So to overcome this, we have flattening layer where feature maps are arranged in the form of single vector. See here, this feature map is in the form of single vector. So all these values are going to the input for the dense layers, and it is going to be like this. So this value is for this node, and this value is for this node, and this value is for this node. It's for this. Like this, each and every value is going to be input for one particular node in a dense layer. Okay. So now I'll move to animation just to show how it works. I'll stop sharing the screen, and that animation actually created by Devang and Robert. Okay, they have worked, and it is also available for everyone to like download the code and they can execute in their own system. Okay, local system. 1 minute, I'll share my screen again. I hope it is visible. Is confirm whether it is visible or not using chat box. Okay, thank you. So okay, it's correct now. Before I start explaining about this, one more thing I want to tell is here they have used in the so here they have used tiny VGGNet. Remember tiny VGGNet. Using this, they have trained this model. Okay, so this is actually a visualization of how things works inside CNN. Okay, so you can see here. Oh, 1 minute. Sorry. Again, now it is good. Okay, so they have used tiny VGNet to train this. I mean, this is the tiny VGNet that trained on 10 images. Okay, 10 different images data set. Okay, so for time being, I'll take this cup, not cup. I'm going to take car into consideration because it is going to show edges exactly or this. Okay, I think now you can see properly. Okay, so they have trained on VGNet. So you can see here we have input image. So you can observe we have 3 different channels: red, green, blue, as I told. It is the first set of convolution layer and activation function. From here we are going to perform pooling operation. Sorry, here no pooling operation. Then we have next set of convolution with ReLU and max pooling, and like that we have many other layers. So now you can see we are giving this image and it is going to say at the end it's a school bus. But how things are happening behind? So if you click on this, it is going to enlarge and it show how it is happening. See here, we have a filter kernel. See, they are telling it is a kernel. It is a kernel. They are applying. See, each and every image is converted into digital image. So we have filter. So when the filter is applied on the image, it is going to extract some features. Say for example, here it is extracting density and the edges. Okay, and you can see here one more thing. This is the kernel values. These are the kernel values: minus 3. 0.3, minus 2.1, minus 2.1, 0.07. All these below values are actually kernel. Whatever the value we are saying inside box is the image. If I move this kernel, the particular point of the image, the values are changing, and the receptive field is going to point to the particular location. See here, it is. If I move here, it is going to point into here. Okay, so whatever the value we are going to calculate, the values of this particular cell in the resultant matrix. Okay, so this is how it works. I'll run this. Let's show. It is moving and moving and moving, and in the meanwhile, it is changing also. Let me start from there. Okay, it is changing. Correct. This is the feature maps we obtained from this convolution, and from this filter. Again, remember, from this filter, from this convolution, particular convolution, using the filter, we obtained this result. Like that, if we apply the filter on the green image, yes, sorry, yeah, see here, it is going to do something else. It is going to extract some other information. Right? It is not extracting same information again. It is extracting some other information. Okay, so like that, same thing will happen here. It is going to extract the feature. Afterwards, all these images, whatever the images, okay, we obtained from the kernel. Remember, same kernel applied on all the images, RGB images. I told no, it is a volume actually. To understand purpose, they are divided. It is going to give this. These are the intermediate images, and this is the output image, final output image from that convolution using the particular filter. Okay, like that we have next set of filters. Here they are using 10, right? So we have 10 feature maps. As I told, if we are using 3 filters, we are going to get 3 feature maps. If you are using 512 filters, you are going to get 512 feature maps. Okay, so this is how it happens. So this particular kernel is going to extract some features out of the image, and finally all these feature maps are combined to produce one. Okay, like that we have 10 different feature maps. Okay, so here we have ReLU, but why we have ReLU? So yesterday I told, so ReLU we have because to ignore, okay, the values which are not contributing to the learning, or in upcoming convolutions, the operations which are not going to contribute, or the what we say, the values which are not going to contribute to the learning are going to be ignored. Say for example here, see here the ReLU, what ReLU will do, ReLU is like this, right? It is going to discard, okay, it is going to discard all the values which are below 0. So it is going to make whatever the values are, negative values are not into zeros here actually. You can see here in this place, this is not going to contribute to, this particular region is not going to contribute to the learning. So they are converting the value into 0. They are taking maximum value. Okay. So now next thing is, you can see, observe here we have some content, but still it is not contributing. Why? Because the filter. It is not because the image, it is because of filter. It is maybe extracting some other features. That's why it is ignoring this color. Okay, don't think that this is not a contribution to image. Okay, not a contribution. It is a contribution, but with respect to filters, we have to think. Okay, so this is how it works. ReLU activation function. I'll run for a while. See here how it is happening. When negative values comes, it is going to ignore that. It is going to convert the value into 0. When positive comes, it just keep the positive. See, just now it is changed the value 0.08, 0.014. It is going to keep the values which are greater than 0. Okay, if it is less than 0, it is going to discard that. Okay, next after this. So we have feature map here. Then next convolution layer, what it is going to do? Again, same thing. We have a feature maps here. We have kernels here. That is filters. We are going to apply we are going to perform same repetition operations. Then we will get this feature map. But remember, in the beginning, we were applying our filters on. Sorry, we had only 3 filters, correct? So we applied, we got the value. Now, for this particular value, we are going to apply this filter like that. We are going to apply on all the channels. See, in the previous step, we had only 3 channels. Here we have 10 channels. That's why I told. So the whatever the feature map we get, the depth of the feature map always. Okay, this is actually a annotation. The depth of the feature map always depends on the number of filters we are using. It is not based on something else. It is the number of filters we are using. Okay, it is actually depends on the number of filters. So we have 10 channels. We are applying 10 different filters on these channels. We are going to get one output. Okay. So like this will work. Again, same thing. You apply ReLU on this particular feature map. You will get one output. And now we have one more. That is so here we have max pooling. So as I told, max pooling is going to take maximum value among the value where among the values of the receptive field. So let's see how it works. If from this location we are going to take maximum value, we have seen right in the previous step while doing ReLU, we have taken max out of two values. But since we are performing max pooling, we are taking maximum out of receptive field where the kernel is applied. Okay, so here the maximum value is this. It is going to be highlighted here in the output feature map. So here it is 0. It is 0 only. Here it is 0.4. It is 0.4. So like this, max pooling is going to work. Okay. Next, I'm going to skip this. So I'll move on to the last layer. It is max pooling. So let's see how it is giving the values. That means how it is voting. How it is voting. So this is what it is. Okay. As I told, we have flattening layer here. Okay, flattening layer where all the feature maps values are represented in the form of vector, single vector. Okay, so it is going to, the value is going to the given feature map is going to pass through one particular value, and it is going to happen. See, if we just place our mouse over this particular link, it is going to show what is the value it is passing through like particular neuron. Okay, it's actually a neuron or a weight. Okay, so almost all are telling it's a school bus. See, all the values are telling it's a school bus. Okay, so now I'm going to show custom one. I'll upload one image from my desktop, then I'll show you how it works. It's actually a cough. Okay, see here how it is performing. Don't worry about the output, because this model is not trained on the animal, okay, given animal, so it is not going to give properly. So but still you can see right how filters are working, how feature maps are generating. And one more thing is, whatever the features learned in earlier stages of the convolution neural network are actually a simpler one. Okay, simple features are going to be learned in early stages of the convolution networks. If you go towards end of the neural network, it is going to learn more depth and complex features. Okay, and I'll upload one more just to show like the same data set. I don't know where it is. Yeah, I'm going to upload this. It is going to tell what it is. See, it is telling exactly what it is, right? No, it is a different image. See, this is the input image they are trying, and this is the output image, right? But still, it is telling the given image is voila. So this is how it works. This is how the CNN works always. And this max pooling and as I told, filters, stride, padding, and we have some other parameters too. All those parameters actually hyper parameters. Okay, used for fine tuning the model, not for something else. Used for fine tuning the model. Remember, fine tuning model. This is how it works. So I'll come down quickly and I'll show how you can go to this link. No problem. We will share later. Here we have hyperparameters. See, input size of the kernel and padding. Sorry, input size of the image, kernel size and stride. So if we have input of size 6x6 and kernel is 2x2, then stride is 2. See, as I increase the stride, okay, the output size comes, it becomes smaller and smaller. If I decrease this, it is going to be bigger. Okay, so if you want to keep same image, so I'll reduce this because in this layout is not going to show. I'll reduce the input size and I'll increase padding. 1 minute. Sorry. Okay. Here, so this is the padding given, correct? So if I move my mouse cursor, it is going to show where the where particular filter is applying on that particular time. So this location is contributing to this particular place. Okay, if I increase kernel size again, one more thing, if I increase stride, the output comes down, output size comes down. If I increase kernel size again output of the particular operation comes down. The dimension of the output comes down. See here, feature map size is reducing. Okay, if I increase kernel size, because when I apply 3x3, this becomes the receptive field. But if I apply 4x4 filter on 4x4 image, entire image becomes receptive field. So whatever the value I'm going to the value I get out of the conversion operation is going to be 1 pixel in the output. Okay, this is one explanation about convolution network, and I want to show one more. It is actually about 1 minute. Stop and again let's share about how filters are going to work behind. Okay. Sorry for delay. I'm searching for the link. Yes, we got it. Yesterday, sir was explaining about kernels, right? So these are actually kernel work. So we have sharpening kernel. We have sorry, I'll come down. I'll show how it looks like. So this is a kernel for bottom sobel. So this is the input image, and this is how the output image look like. Then we have sharpen. So this is how sharpen filters are going to convert the input image into sharpen image. Then we have top sobel. Then we have blur. Okay. Then we have emboss. Then we have identity. Okay. Then we have outline. So like this, different filters are going to perform different operations. So one more is more visualized explanation for the convolution. Actually this model is actually trying to identify digit bits between 0 and 1 to 0 to 9. Okay, I think it's 0 to 9. So if I draw any one digit here, it is going to predict what it is. You can see here, right? It is predicting it is whatever I done on the given space. It's 2. Okay, so this is how it looks like actually. You can see here. So how it is the convolution layers are performing convolution operation, pooling operation, and flattening operation. So it is about the visualization animation of the working. So again, I'll come back to slideshow. Okay. So okay. So here we have one more explanation, that is feature maps. How to calculate the feature maps size. Okay. So imagine, so if we have an input, of size, sorry for not writing properly. then 48. So the size of this input is 48 or 48, and number of channels are 3. Okay. So now we are going to make use of this formula. To calculate or to determine the next feature map dimension or resolution of the feature map. Okay, so from here we are going to apply. So you can see here we have 48 or 48 and 3. So number of channels are 3. I'll just take NW equal, that is width, and height equal to 48. Okay, and I'm going to use filter of size 3 × 3. Okay, stride is 1 and padding is 0, and I'm using 20 filters. So what will be the output of this operation? Simple. You substitute the values here. So we have n in, that means the size of the input is 48 plus 2. Padding is what here? The parameter is 0. So into it is actually 0, multiple is 0. Then we have k. K means actually a kernel size. It is 3 × 3. So 3 it is. N divided by stride plus 1. Okay. So now we have 40. This is actually 0, and 48 minus 3 is 45 divided by 1 plus 1. Output will be 46. So output of this operation is we are going to get a feature map of size 46 × 46. Then how many channels we are going to get? Number of channels are actually is equal to number of filters we have used. Okay, number of filters we have used here. So this is actually going to be repeated again and again. Okay, if I do same again. So if I use, let's take one more example of with a different kernel size. If I take filter of size 7 × 7, okay, 7 × 7. Again, strides are same. Same. So how much we will get? What we will get as our output? Sorry, I'll take stride as 2. Then only we will get to know what is the difference. Okay, so it is 46 plus 2 × 0 minus 7 divided by 2. So we are going to get 20 × 20 into filters. So if I use 20 filters, the depth of the filter is going to be 20. If I use 40 filters here we are going to get 40. The difference is simple. As many filter you use, you are going to get those many channels. So this is how it works. Okay. So as I told, I explained how it comes. Then why we have 1? Simple. See, if you are using, imagine if you are using 3 × 3 input image and you are applying 3 × 3 filter itself, then what is going to be our output? So I'll substitute here. So 3 × 3 input size plus no padding, then our kernel size is 3, then stride is 1. Okay, it is going to give the value 0 actually, because it is 0. This is and this one gone, so 0. But as I told, if the input image and kernel is same, size is same, then we are going to get 1D image. That is, sorry, 1 + 1 image output. Okay, that's why we have 1 here. So if we have the filter size and the image is equal to same, at least 1 should be there. No, that's why we have 1. Okay. Next is dropout. So here it is very important to know why we are dropping. So why we are dropping is because like I told, no, some of the while explaining that showing value, some of the values are not going to be like contribute to learning in upcoming layers. Like that, we'll be having some nodes which are not going to be worthful to keep in the network, and that may create some problem like overfitting problem. Okay, to overcome that overfitting problem, we are using dropouts. So usually this dropout value like varies between 0.5 to 0.8. That actually always nearer to 1. Okay, nearer to 1. So this is why we are going to use dropout. That means we are going to drop some nodes, some like some of the neurons in the dense layers. It is not a convolution actually talking about. It is actually a dense layer. Okay, it is not a convolution layer. It is a dense layer I'm talking about. We are going to drop some of the nodes to learn to make the to work in the problem of overfitting. Okay, so next is learning techniques. We have actually 14 or around 16 or 14 different learning techniques in the present world. Okay, we have many too. And I have explored 16. So I'm sharing my experience here for few. Okay, so now we all know, everyone knows actually supervised, unsupervised, and reinforcement learning or semi-supervised. I'll repeat this and I'll concentrate on few. So we know that what is supervised learning. So this is like how baby learns, how we teach a baby. Okay, we are going to give a flashcard to, we are going to show a flashcard to baby. This flashcard will have images of animals or characters or anything. Okay, we are going to show a baby a flashcard. That means we have a card with us and name for that. Okay, name for that. That means a label is there, label is present. Okay, we are going to show baby this card and we will tell this card is this. Say for example, this is dog. We will tell baby that this flashcard is dog and this flashcard is elephant. Okay, so this is the idea behind this actually supervised learning. We are going to give input data as well as the labels, So we are going to train the model using these two. So finally, this model learns the features out of the given input and matches with the labels, and it fine tunes. Okay, finally, after training ends, it is going to predict unlabeled data. Okay, these are supervised works. So here actually we are using classification purpose and or we have in object detection we use for feature extraction there and all we use this. Okay, so next is unsupervised learning, where we are not going to use any labels, but we will give data. We will give input based on the patterns, based on the shape, based on the some other features. The model itself going to group or creates clusters based on the features, based on the shapes or color. It is going to create clusters and it is going to give output. Okay, and here we don't have target value here, we have only input. So you can see here, so birds are clustered in one in group in one side, and animals are, that means cat and dogs in one, and sea or we can aquatic animals in one side. Okay, so next is reinforcement learning. So reinforcement learning is like the best example. The best example is this: how dog learns. Okay, how dog learns. So we all know while training a dogs, what we will do, not only dogs, even if we take circus, if we take any other like how they train our Jambu Savari, Abhimanyu, or some other animals, we other elephants we have, no, how they train. So what dog will do, we all know, and we have seen owners will throw a ball or stick. So dog will pick that ball or a stick and gives that to owner. But what it is doing, we will instruct that to do. If it fails to do, we are going to hit that first. That is what reward is. So So for a particular state, it is performing action. So state is owner throws some ball or stick, it is sitting. So the reward it has got is beating. Okay. At the same time, if it goes and brings ball or a stick, it is going to get a reward. That reward may be eatable things, whatever it may be, a biscuit. Okay. So this is how reinforcement learning works actually in the real world. Okay, it is going to perform some operation. For that operation, it is going to predict something. For that prediction, it is going to get some rewards. Okay, this is how reinforcement learning works. I hope it's clear. So next we have semi-supervised. As name itself says, semi-supervised. Here we will be having large amount of unlabeled data and small amount of labeled data. So the model is going to learn. This model is going to learn using. First, it is going to be trained on this particular data set. Okay. Then it is going to be trained on this data set. So finally, this model will label the unlabeled data set based on the what we say the knowledge has got gained from this labeled data set. It is going to label like this, that is called as pseudo labeled data set. Then finally, we will train our model using small data set as well as that means the whatever the knowledge we have here now plus the pseudo labeled data set. So we are going to train on this data set ultimately. It is going to learn. Actually, it is very important the self-supervised because it is actually trending now. What is self-supervised? Here no label, nothing. Okay, here but we have some automated operations in between the convolution before applying to the convolution layer or to the model. We have some operation where the operation is going to automatically label. It is not going to label like this given image is cat or given image is a dog or something like that. It is going to label like this the values. Okay, so this represents 0, this represents 90, and this represents 180. See here, this is also cat, this is also cat, or maybe I don't know what it is. It is also cat. Okay, ultimately we are going to combine these two, and we will give this particular data to convolution network, and it is going to learn features, and it is going to perform the operations. Okay, so this is about self-supervised. So next, this is again very important, and this is actually a future. This is actually a future. It is really going on. Okay, what is active learning? This active learning is like we have data. Okay, we are going to perform something. That something is like is nothing but model. Okay, we have data, we have model, we have the model is going to do something, and we have here someone. Okay. And again it is going to do the same thing. That's why it is showing. It is like we have data set, we have model. This model is going to ask this person is called actually annotator. Okay, it is going to predict and it is going to send query to this person asking that is this correct or is not correct, like that is going to ask. That is what it is. Click query. Use learning function to select the next sample. Okay, it is going to ask query, so he is going to do something, that is he is annotator, so he is going to send information to the model, then it repeats. Okay, so why we need this active learning? Actually because in the medical field, if we have X-ray image, okay, if we have X-ray image or brain MRI, it is not so simple for a technical guy or a model to understand this is correct or it is not correct. So we need someone who is expert in that area, right? So that's why you can assume that this person is an expert in the medical field. So this model is going to show some information to or some outputs to this person. So he actually goes through that output. Then finally he is going to correct the output. This is not correct. So for example, it says here is a lesion. Okay, like this it look like, but it may be this much weak. That's how it works. Okay, we are going to discuss in a segment as a segment models. Okay, the final one is transfer learning. Again, it's a trending topic. Okay, the transfer learning is like like whenever I explain to students, I say a funny thing that in the olden days, saints used to tell whatever I learned, I'm going to not transfer to you. Like that it is actually. Okay, so here we will be having two models. Here we will be having two models. One is pre-trained. Okay, pre-trained model, and one more is model which is going to train, which is going to use the knowledge. Okay, for example, here we are training a model on this. Actually, traditional learning actually, we will train a model on this and this. So knowledge is here. So this one particular model is going to do a particular task. Okay, so but here we have a model, okay, which is trained on some other data set, a huge data set. Okay, and we are going to utilize the knowledge learned by this system for some other purpose. Say for example, here we have huge data set, and we will train this data set. We will train this model using this data set. Say for example, ImageNet or COCO or MRI data set is there. That also we can imagine. Okay, take it as example. So we are going to train model on this data set, and we have some other column where we have less number of samples. We have less number of samples. Okay, we are going to make use of these samples to predict, but still, since we have less number of samples, okay, so then after this, so we are going to make use of this knowledge. That means we have a pre-trained network here, pre-trained network knowledge here. We are going to utilize this knowledge. That means we are going to combine the knowledge to this learning system, where we are going to utilize same network. Say for example, this is a network. This is a neural network. So this is already learned. This is already trained on some other data set. This network is already trained on some other data set. So we are going to freeze these layers, okay, few layers, and we start fine-tuning this network using this data set, a small data set. So what will happen if you use transfer learning? What will happen? What is the advantage of doing this? Is time saving. Okay, one is time saving. Computational power is not required. Too much of computational power is not required. Okay, not required. Then we ultimately we are going to skip some of the parameters, and we are going to train only some few parameters of this model. Okay, this is how the transfer learning work. So we'll be having transfer knowledge of some other network. We are going to utilize that in our network. That means we have two ways. One is fine-tuning same model, and one more is utilizing features. This fine-tuning is what I showed here. Utilizing features means this is what utilizing feature is. Okay, so I'm using this feature for this particular network. Last one is ensemble learning, where this is the last slide for this session, and then we will take a break. Then again we will come back for next session. Okay, so this is ensemble learning. Actually, what it is means, here what we have now, these models are actually called as weak models. Okay, so we have some input. We are going to give this input to these weak models. All these models are going to exploit the input and it's going to predict something. All these models are going to exploit the input. It's going to extract the features and understand what the image is or what the input is. Then we have models here. So these models are going to say given image is 1, given image is 1, given image is 2, given image is 1. So based on majority, we are going to select output. Okay, this is what it is. This is how ensemble learning works. Nowadays we are seeing this also ensemble learning also, where they call it as ensemble models. Okay, so remember these are all the weak models. Okay, the prediction of these models are not acceptable for alone as a model. Okay, this is how it works. Okay, so we'll come back. So attendance link will be shared in 2 minutes because I am the one who is going to share. So thank you. So we'll come back for next session, and at that time I am going to answer all the questions. Okay, because I need break. I'll come back. Thank you. But I am not going to end the meeting. Wait for 2 minutes. I'll share the link.
Thank you. What will those? If you have any questions, you type in the chat box. Okay, I really appreciate your effort and time to share your knowledge on CNN. I believe that every participant are benefited from your presentation as Saba conductors. I personally appreciate your approach to content that's regarding all the particularly which will be presented in the slides that so has to just to learn about more on CNN models. Thank you, Nagaraj, for your wonderful and informative sessions. Thank you very much. Link will be shared. That attendance will be shared within the few seconds. We give the attendance also.